Mathematical analysis of transport of contaminants through unsaturated porous media in applied soil column experiments. Abstract. The main objective of the study is to provide mathematical model for better understanding of transport of pollutant through unsaturated and saturated porous media. A mathematical model is an important tool and can play a crucial role in understanding the mechanism of groundwater pollution problems. It is a simplified description of physical reality expressed in mathematical terms. Mathematical models that attempt to simulate atmospheric processes involved in groundwater pollution are based, in general, on the equation of mass conservation for individual pollutant species. Such models relate in one equation the effects of all the physical aspects and dynamic processes that influence the mass balance on groundwater, which include transport, diffusion, removal of pollutants and loss or transformation through chemical reactions. Keywords: integral transforms method, mathematical modeling, advection dispersion equation, saturated porous medium, unsaturated porous media, heterogeneous flow. Introduction. Solute transport in the unsaturated flow is determined by the phenomena of advection and hydrodynamic dispersion, both of which depend on the flow field. Hence, a general model of solute transport must include the equations for flow and solute displacement with terms appropriate for physical, chemical, or biological interactions of the solute with the soil environment. The increasing demand for water for domestic, industrial, and agricultural purposes is placing greater emphasis on the development of groundwater resources. The exploitation of groundwater resources at some parts of the country induces degradation of groundwater quality as well as the discharge of untreated effluents which add contaminants to the groundwater system. Water is the most precious resources provided by the planet Earth to humanity. Water forms an essential ingredient for the existence of all forms of life, and is, therefore, considered to be the lifeblood of biosphere, and controlled growth of population and rapid industrialization have resulted in increased demand for water in human activities. Water is available on the earth either on the surface of the ground, surface water, or below the ground, surface groundwater. The importance and management of these two types of resources have been studied independently by many researchers over the past 2 decades. Nowadays, researchers have felt the need to study both the systems together for better understanding of the interaction between surface water and groundwater in the unsaturated zone, which lies above the water table and up to the ground surface, linking the two types of resources mentioned above. For mathematical models, the earlier works made use of Green's theorem and stochastic process for solving the partial differential equations, resulting in complicated solutions. In the present work, we have made use of the integral transforms, moving coordinates, and Duhamel's theorem to solve this equation, which simplifies the solution to a simple form, considering different parameters like adsorption, non-adsorption, chemical reaction, and radioactive decay. For the same model, the results are compared with the experimental data. Modeling studies. The mathematical models consist of integrated hydrological and solute transport models and are used to simulate contaminant movement and subsequent uptake by plants. The hydrological model is based on Richards's equation for the transport of water through soil in response to the forces of gravity and water pressure. Richards' equation relates the change of soil moisture content to the hydraulic flux divergence. It assumes that water flow can be represented by Darcy's law, whereby the flux is related to the product of the hydraulic head gradient and a nonlinear hydraulic conductivity parameter which depends on the moisture content of the soil. One major influence is on the abundance of films, and is strictly geometric. From dimensional considerations of geometrically similar porous media, both the specific surface area per unit volume, and specific perimeter, PS, grain perimeter length per unit cross-sectional area, scale as 1. Therefore, at low water saturations, thin film flow is localized on grain perimeters, which per unit bulk area increases as grain size decreases. A functional relation between PS and can be obtained for monodisperse packs of spherical grains by first determining the number of grains N0 intercepting a plane of unit area A0 in a porous medium. Such a plane will intercept grains with centroids located within a distance of /2 on either side of it. Therefore, grain centered within a reference bulk volume of unit cross-sectional area A0 and thickness will have perimeters that project onto the unit cross-sectional surface. With a porosity n, the solid phase volumetric fraction of 1n is equal to the ratio of the solid volume per unit bulk volume. For the reference volume of A0. In the modeling of the underground transport, first question is how to handle the fluid flow. In all models reviewed in 23 and 15, and further studied in 14, we remarked that the concentration of the transported contaminants is such that the flow is not affected. This means that we should study the effective flow before looking at the mass balance equations for the transported species. All flows could be considered as incompressible. For the multiphase flows, we can't say much about the derivation of the microscopic models from the first principles. We refer to the review paper of Bourget 12 and to the calculations for the flow through a Singapore in 19. To the contrary, homogenization of the microscopic models was studied with success in many papers. We refer to 9 and 18 for the two-phase flows in periodic geometries and with the permeability of same order, to the article 10 for the random case and to 11 for the two-phase dual porosity model. Very frequently, solutes are transported by an unsaturated flow. Single-phase unsaturated flows are described by the Richards equation. Even if it seems that the equations describing the two-phase flow of water and air are more realistic, the Richards' equation is widely used and in the hydrochemical computer codes one should solve it in a heterogeneous medium. Hence, in order to have an effective equation for the velocity and the pressure, we study the homogenization of the Richards equation. The Richards equation in the dual porosity case reads as follows, CEG 7. Where d is a small positive number, Pe are the unknown, scaled, pressures, J is the water content and K is the hydraulic conductivity. Let us note that we have two functions J and K. Each J is a C1 strictly monotone increasing positive function on, equal to ds for S0. Each K is a C1 increasing function defined on 0, 1. They are positive and strictly monotone increasing for JQ0. They could be 0 on 0, Q0. Let V equals VAA 1/2 H1, W, V equals 0 on G1. Proof. Proof of the proposition follows the lines of the Article 5. It should be noted that the conditions on the data guarantee the non-degeneracy of the coefficients. Next we use the results from one presented in the introduction and extend PE to W. The extension PEP satisfies. The real difficulty is in identifying QM. Let us note that PE doesn't converge strongly and oscillations are likely to persist. We proceed by using the method of periodic modulation as in 11. It was introduced in 6 and we repeat the definition. 3. Modeling transport, diffusion, and adsorption of chemical species. We are going to assume that certain chemical species are dissolved in the fluid. Their concentration is sufficiently small and the fluid flow is not affected. For simplicity of notation we write the equations for just one species. The generalization to M substances is straightforward. The conservation of mass law is where VE equals KF, JF, PE, AAPEAE3, is the filtration velocity, VEUE is the convection term, DAUE is the dispersion and diffusion term and F, UE, represents the chemical reactions. The simplest way to include adsorption effects is to introduce the concentration UE of the substance absorbed on the pellet surface. It is reasonable to suppose that the actual adsorption rate B depends on UE and UE. Thus we have where B is a Holder continuous function of U and U. In order to complete the model we add an equation describing the dynamics of the adsorbed concentration UE which reads. Using the results from 17 we find out that UE converges in two scales to the solution U of the following problem. We suppose 4 numerical simulations. We would like to point out the effects of chemical reactions. Consequently, without losing generality, we consider only a saturated flow in W equals 0, 2p, 2 and the periodic boundary conditions for the concentrations. To obtain a precise approximation to the saturations, we approximate the spatial derivatives using the pseudospectral method. More precisely, we write U and U in terms of the corresponding spectral Fourier basis. The unknown functions in the nonlinear terms are evaluated in the collocation points, coming from Fourier's grid of the size 256 AA256. Then using the inverse FFT, the nonlinear terms are written in the spectral basis. In the time discretization, we integrate exactly the linear terms, A, the diffusion convection term in 50, and B, the linear term containing U in the adsorption rate B. For the nonlinear terms we use a third-order explicit Adams-Bashforth scheme for F, U, in 50, and an implicit third-order Adams-Bashforth scheme for B, AA, U, AA, in 54. After scaling the equations with the characteristic time Tc equals 2AA104, we take the time step 10 to 3. This numerical approach was developed in 2D turbulence simulation by Robert and Rosier, C22, and the method is very robust for the nonlinear coupled transport and diffusion. We present two numerical experiments. They are with same data, but with different isotherms. The data are given by the following table. F, U, is taken to be linear. The results are at the figures which follow. They show important effects of the transport on the evolution of the concentration profiles. Also diffusive effects depend very much on the choice of the isotherms, as visible on the figures. After these calculations, which correspond to the simplest homogenized model, we are planning to develop a numerical method for the unsaturated flow, to add the surface diffusion in the modeling of the adsorption and to include the effects of high Pa copyright clit number. The basic challenge is to develop fast solvers for dual porosity models, and for more details we refer to the recent article 2. Waters in Mono Basin, California, Newman and Dries, 1995. A follow-up study was presented to reassure and re-evaluate the 36 content at several previously studied sites in the Great Basin, Phillips et al., 1995. Soil water chemistry and isotopic data were presented from 3 deep vadose zone boreholes at the Nevada test site to quantify soil water flux and its relationship to climate, Tyler et al., 1996. Tracing techniques and core data were used to study the temporal and partial variations of the soil water flux and recharge during the last 120,000 years. Natural variations of stable isotopes were used to study infiltration in clay soils and groundwater recharge in the small drainage basin of Barago in West Africa, Matthew and Bariak, 1996. The isotope analyses led to the characterization of 2 separate infiltration processes as well as 2 recharge processes. Stochastic modeling and analysis. The spatial temporal averaging method was used for modeling transport in porous media with a non-homogeneous distribution of elementary domains in the spatial temporal space, he and Sykes, 1996. Several averaging theorems and corollaries about the averages of spatial and temporal derivatives were presented and rigorously proved. The real space expressions for second-order mean velocity and velocity covariance in 3D, statistically anisotropic media were derived, and the effect of higher-order flow correction terms on first- and second-order reliability methods were applied as alternatives to Monte Carlo simulation in the probabilistic analysis of groundwater contaminant transport and remediation, Hamed et al., 1996. A 2D-FE model was interfaced with a reliability analysis program that provided the probability that a contaminant exceeds a target level at a well. Covariances of velocity, head, and log, hydraulic conductivity, under quasi-steady flow were developed, and their effect on adventive transport was examined, Zhang and Newman, 1996a. Results showed that temporal fluctuations in the direction of the mean velocity cause longitudinal dispersion to decrease and transverse dispersion to increase. Probability distributions of travel times were developed for 1D, vertical, convective solute transport in field-scale soils under unsteady and non-uniform flows. Approximate ensemble probability distribution functions of conservative solute travel time were derived directly from the convective transport stochastic partial differential equation. A higher-order theory was presented for steady-state mean uniform saturated flow and non-reactive solute transport in randomly heterogeneous porous media, HSUETAL, 1996. Results show significant improvements compared with lower-order theories. Dogon solution for transport in heterogeneous porous formations was extended to the case of finite PE, Fiore, 1996. It was suggested that pore-scale dispersion matters only with reference to transverse spreading, and that Dogon solution, valid for PE equals 00, was an adequate approximation in a wide range of finite PE. General equations for the first two moments of the particle trajectory were derived for the problem of transport of inert solutes in random non-stationary velocity fields. It was shown that the equations can be solved analytically for the case of quasi-unidirectional mean flows, and the theory was applied to the case of transport in media displaying a linear trend in the mean log conductivity. The general expressions for the time-dependent ensemble averages of the second spatial moments, A, and the effective dispersivities Y were evaluated to study the effect of initial plume size on A and Y in 3D heterogeneous isotropic aquifers, Zhang, YK, ET at 1996. Results confirm that A and Y approach their respective erotic limits as the size of the source increases, and that transverse lengths of a source were more important than longitudinal length for the erotic condition to be met. The exact and approximate deterministic partial differential equations of the time-space evolution of mean, 2-point moment, and end-point moment solute concentration for conservative solute transport by steady and unsteady groundwater flow in a heterogeneous aquifer were developed in the real space-time domain. The derivations were performed by means of the cumulant expansion method, combined with the calculus for the time-ordered exponential and with the calculus for the Lie operator. A fully nonlinear analysis of the integral differential equation for the spatial second moments x of the ensemble mean concentration in a heterogeneous aquifer was carried out by solving the nonlinear integral differential equation for x numerically and iteratively, Zhang and Qi, 1995. The effects of log, hydraulic conductivity, variance, PE, and anisotropy then were investigated. Conclusion. A discussion was presented regarding a paper on inappropriate use of analytical fate and transport models to estimate the A. Stochastic modeling approach and Monte Carlo simulation were used to characterize the uncertainty in migration pathways in geological media surrounding a hypothetical buried water repository in Bedfordshire, UK, McKay, R. ET at 1996. The coupled effects of porous media heterogeneity and flow unsteadiness on transport were investigated using a stochastic Lagrangian approach, where log conductivity was modeled as a space random function and flow unsteadiness was considered deterministic, affecting the magnitude and direction of mean head gradient, Dogon ET at 1996a. By applying the model to the case of a periodic variation in the flow direction, it was shown that unsteadiness has an insignificant effect on the longitudinal spread, whereas it strongly affects the transverse spread. An experimental velocimetry technique based on particle image analysis was used to perform a Lagrangian description of non-reactive pollutant particle motion in a 3D saturated porous medium, Sindis and Viotti, 1996. Statistical analysis of the experimental data allowed for estimation of velocity and displacement probability density functions, velocity component correlation functions, Lagrangian integral scales, and mechanical dispersion coefficient tensor components. A recently developed exact Eulerian Lagrangian theory of advective transport in space-time random velocity fields was extended to account for anisotropic local dispersion, Zhang and Newman, 1996b.